Hello, class. Okay, so I'm going to do a new topic. We're going to talk about resistance. So last time with this Druid model, we showed Ohm's Law is valid for a conductor like copper, or just any simple metal. So let's say we have an electric wire. Say we apply an electric field E. There's going to be a potential difference between the ends of the wire. And we know electric fields go from high potential to low potential. So let's send the right end of the wire, let's set that to 0. And the left end, we'll just say it's V. And the length of the wire, we'll say is L. And let's apply Ohm's Law. We're going to write this in a kind of a different form that you may be more familiar with. So to start with, the electric field, we're just looking at magnitudes here, so forget about the minus. In our basic formula, we have the rate of change of potential in a particular direction. So like over distance. Now because this is a constant electric field, this reduces to simply delta V, or the way we wrote it, V over L. So for a constant electric field, E is just V over L. And let's write Ohm's Law. We can also write E as J over sigma. From Ohm's Law. And let's solve this for potential. So that would be J times L over sigma. Now also the current density is the current over the area. So let's plug that in. So we have I L over sigma A, and one more thing, let's do okay, so what we have here, we have a wire, electric field across it, and we see that the potential difference between the ends of the wire, L is the length of the wire. Remember, sigma is just a property of copper. Like we did a problem where we just have a value for sigma. And A is a cross-section of this wire. And so for any particular metal, or for any shape, it depends on the area and the length, this is going to be a constant. And so we found that the potential is proportional to the current. That's another way of stating Ohm's Law. So if you double the potential between the two ends of the wire, you're going to double the current. Now that seems perfectly reasonable. However, I should point out that this is not actually true in general. There are many devices that do not follow Ohm's Law. One very common device is just a light bulb that does not obey Ohm's Law. And there are, maybe to a somewhat reasonable approximation it does, but there are other things that don't behave anything even remotely close to Ohm's Law. You think of like, there's devices called diodes, which only allow current to flow in one direction. So you could have, apply an electric field, and in one direction, you'll get a very significant current, but if you just reverse the direction of the electric field, you'll get no current, or virtually zero. So it can even depend on direction for some materials. So, Ohm's Law, this idea that the potential and the current are directly related to each other, they have a linear relation, That is only true for certain materials, certainly not true for everything. I want to play around with this a little bit more. If we look at this wire, sigma is a property of what this wire is made of like copper. Maybe you could have aluminum, whatever. So, and L and A, those are just the dimensions of the object. So I want to kind of separate them. One thing though, we have sigma in the denominator. It's not really necessary, but we're going to find another variable called rho, which is 1 over sigma. This is called the resistivity. And so with that definition, we have V is equal to rho L over A times I. And this quantity here we call the resistance. So the resistance of, say, a wire, that's going to depend on the length of the wire. Longer wire, more resistance. In a primitive model, you can think more collisions as it, remember when the electrons collide, you know, the electric field is doing work, so it's giving energy to our system. But when the electrons collide with the atoms, they give up that energy, turn it into heat. And so, yeah, longer wire, you'd have more collisions, so more resistance. It's inversely proportional to the area. So if you have a thicker wire, it's, you know, easy. Think of it, you can maybe spread out the electrons more. Although the electrons don't interact with each other, but not in any way that matters anyways. So, yeah, but a thicker wire, less resistance. And it also depends on the material. And resistivity, this is the one that you can find tables for. So you generally don't find tables for omega, but again, resistivity, much easier. Now the units of resistivity, well, we measure resistance in ohms. So the symbol is this Greek letter omega. So again, remember this is Ohm's law, so they named the unit of resistance after ohm. So, yeah, the unit of resistance is the ohm, and resistivity then has units of ohms times meters. So if you take an ohms times a meter, multiply it by a meter, and divide by a meter squared, you'll get an ohm. So those units work. So basic SI units of resistivity are ohms times meters. So resistivity is a property of the material itself. Like you can look up the resistivity of copper or aluminum or gold. And the resistance, that's a particular sample of, say, copper. So it has a certain length and a cross-section area. Now, I said Ohm's law doesn't really hold up for every material. However, Ohm's law is extremely useful, and so what they've done is we define resistance. I'll use this mathematical notation. So when you have like 3 equal sign, that means we're dealing with a definition. So R is exactly equal to, oh, I think I got that backwards. Yeah. So we define resistance to be the potential over the current. And by defining it that way, that makes V equals IR automatically valid. However, by doing that, what that means is that resistance is no longer necessarily a constant. So it can depend on other factors. So Ohm's law now is always valid just by definition. V equals IR, that equation, you can always use it. but resistance may not be constant anymore. Now, in many cases, the resistance will be constant, and we call those ohmic materials. So if the resistance is constant, that means that the current is directly proportional to the voltage. You double the voltage, you double the current. And if that is true, then we say that we're dealing with an ohmic material. If it's not true, we have this very creative name for it. We call it a non-ohmic material. And so Ohm's Law, written in a much more familiar form. And again, you probably see it this way first. V equals IR. And we wrote it down on our equation board. Because this is actually a very nice way of doing it. If you don't look in the microscopic details, but we took that approach of looking at what's going on a microscopic level. So we took a different approach and got this result first. But you can also just start out with Ohm's Law, kind of as an experimental result. Now, I want to talk about one more thing when it comes to resistance. I mentioned earlier that if a metal like copper is a crystal, the atoms make up this periodic structure. And if you had a perfect lattice, every atom is exactly where it's supposed to be, and it's a perfectly repetitive object, like every atom, they have this pattern and they're just where they're supposed to be, and there's no impurities. There's no extra atoms inside, or you don't remove an atom and leave a gap. So, perfect lattice, there would be no resistance. An electron or current could just flow freely with zero resistance. Now, you might have heard of the term superconductivity. Just to be clear, we are not talking about superconductivity. That happens for a completely different reason. But this perfect crystal is not something that can exist. For one thing, everything has to be perfectly in its place, every atom. We know atoms do not remain perfectly stationary. There's internal energy which shows up in vibrations of the atoms. And so if you just took a picture, the average location of an atom forms a periodic structure. But if you take a picture, because of the vibrations, they're not going to form a perfect lattice. And so there is going to be resistance to the motion of these electrons. And the higher the temperature, the more energetic these vibrations are. So we might expect resistance to depend on temperature. More energetic vibrations, the atoms are going to be more out of place. And there is actually a dependence of resistance on temperature. I'm going to write this down. I'll write down the equation. So this is a good kind of empirical result. It's very good. It's not like we theoretically derive this result, but it works. One of those kind of things where we just fit this and say, yeah, this works. So let me get out the book and look at this table. Now we have a rho naught. That's resistivity, but with a subscript. So this is a particular value for the resistivity. Basically, the resistance depends on temperature. So this is the resistivity at a particular temperature. That temperature would be T naught. And the temperature is usually chosen to be 20 degrees Celsius. Now this alpha, that's something you would look up in a table, which... Yeah. So, in the book, it's table 26.2. Resistance. It has certain materials, and then it has the resistivity at 20 degrees Celsius, and the temperature coefficient alpha, which has units of inverse Celsius degrees. Because this has to be just a number. You have 1 plus some number. So alpha times a temperature has to just be dimensionless. So the units of alpha are inverse Celsius degrees. So T naught is 20 degrees. R naught is what you get just from looking in this table. So you always read the fine print. It's usually taken to be 20 degrees as a reference, but maybe if you look it up somewhere else, they have a different value. And you can see that the resistance does actually increase with temperature. Like if we're at a temperature higher than 20 degrees, then this part in parentheses is going to be positive. And so the resistance will be the resistivity times 1 plus some positive value. So we're going to have a higher resistance. And again, that's what we should expect based on this theoretical idea, that resistance is caused by imperfections in the lattice. And again, I just want to stress that you might think just by lowering the temperature to 0, you can make this disappear. But even that would not work due to quantum mechanics. You might have heard of the uncertainty principle, which basically says the product that you can't measure anything perfectly. And if you look at the position and momentum, there has to be an uncertainty in the position. And there also has to be an uncertainty in the momentum. And what Heisenberg determined, that these are fundamental, there's no way around this. That no measure, because in order to measure something, you have to interfere with it. You have to interact with it, which will affect what you're trying to measure. And what Heisenberg discovered is that this product has a minimum value. It's greater than or equal to some constant. Well, really Planck's constant. But we're not going to get into that. But the point is, if you say an atom has a definite location, or very close to that, you make delta x very small, then there has to be a significant uncertainty in its momentum. So if you narrow down the location of the atom very precisely, that means that it could have a large momentum and it's not going to stay there. And so you can never get everything to settle down perfectly. That would violate this very fundamental rule in physics that has no exceptions that we know of. So that's called Heisenberg's uncertainty principle. And personally, the reason I'm so confident that the uncertainty principle is an actual fact of our universe is Einstein hated this. When Einstein came up with this idea in the 1920s, Einstein spent the rest of his life arguing with him and really trying to disprove this. And it's kind of a funny story. They were at a physics party, and Einstein came up with an argument where you could actually violate the uncertainty principle. And his argument was so convincing, I'm not sure if he was arguing with Heisenberg or someone else who was a big fan of arguing in favor of the Heisenberg uncertainty principle. But this person was very disappointed because Einstein won. He found an exception to the uncertainty principle, and then left the party. And later on, this guy figured out that Einstein was actually wrong. That he kind of mistaking something into account, and the uncertainty principle holds up after all. So again, we have to accept this as a fundamental fact of the universe, and if you can disprove that, well, you managed to pull off something that Einstein couldn't do, despite trying very hard to do so. So yeah, this, you might think, lowering the temperature down to 0 Kelvin, that'll get rid of all the resistance, and if you're familiar with superconductivity, it only works at low temperatures, but superconductivity is something completely fundamentally different. It has nothing to do with this equation we wrote down. Okay, so I think I'll leave this one here, and that'll be it for resistance.